Okay, good morning. This is Professor David J. De Los Reyes. Okay, the date for today is December 7, 2023, and the time is around 12:37 a.m. Okay, my topic for this session will be a continuation of my long video format discussion on AC machines, and I am now on lesson number 65. We are almost done with alternator. Uh, it's easy for us to study alternator because alternator is always similar to the so-called circuit to a transformer. Transformer and alternator are actually cousins. Okay. So for tonight, let's try to discuss AC machines, lesson number 65. Okay, let's proceed. The subject matter for tonight will be, or for this morning, will be AC machines, lesson number 65, and the title of the subject matter will be alternator efficiency. The last time around, we already have discussed the so-called percent voltage regulation of an alternator. Percent voltage regulation is a concept on how we determine if an alternator could, what we call this, generate a stable voltage. So for tonight, we will be discussing alternator efficiency. Alternator efficiency is different from voltage regulation because alternator efficiency actually, if we try to define efficiency in general, it should be power output all over power output plus total losses. So we will be using this concept in the so-called determination of the efficiency of alternator. So efficiency in general for alternator, this is designated by Greek letter, uh, big letter N. Okay, it's a letter N, but it got a longer tail to designate that this is efficiency. Okay, so in general now, for the study of alternator, this designation represents efficiency. And if we try to read the equivalent of this in terms of an equation, we always relate our concept to an equation. So for us to easily, what do you call this, remember that concept, that is efficiency will be capital letter P with the subscript O, meaning power output, all over again capital letter P with the subscript O, meaning power output, plus capital letter TL. And TL actually represents total losses, and efficiency is always multiplied by 100%. So this is multiplied by 100%. So this is actually the general equation or formula on how to compute for the efficiency of an alternator. But in the computation of the power output, this is just a simple one. Because if we are given the total apparent power of an alternator in terms of kVA, okay, we'll just multiply this by the, sorry. If the total apparent power of the alternator is given in terms of kVA, to compute for this power output can be written as simply S, okay, times power factor. And by definition again, from the study of transformer, and we still use it under the study of alternator, power factor in general is actually power output all over S. Okay? So under the study of transformer or alternator, power factor is the ratio of power output in kilowatts all over apparent power in kVA. If this is watts, they should be volt ampere. If this is kilowatts, they should be kVA. If this is MVA, megawatts, they should be MVA. Okay. So in here, I place capital letter P with the subscript O. This should be O, letter O. meaning power output, should be the total apparent power times the power factor of the alternator. And TL, this is a complicated thing because the manner in which we will determine the total losses. Okay, if we try to read the equation here, it should be the rotational losses plus the electrical losses. We are familiar with the electrical losses, but for rotational losses, for the meantime, we do not know how come we will be computing for the rotational losses of an alternator. For transformer, this rotational losses is actually missing. This is actually zero for transformer. But for alternator, okay, the alternator is actually the one rotating to generate voltage. There is a physical movement, so there should be a rotational losses. So there is rotational losses for alternator. And for tonight, we will be giving a little bit of storytelling on how we will determine the rotational losses. Okay? But before we will discuss how we determine the rotational losses and the electrical losses, we'll try to read this legend here. That is, this capital letter N represents efficiency. Capital letter P with the subscript O meaning total power output. Capital letter TL is the total power losses. And capital letter S is the total apparent power. And PF, okay, is just the same. The power factor we are mentioning under transformer is the same as the power factor we are mentioning under alternator. So PF here represents power factor. So before we will discuss how the rotational losses and electrical losses in the other losses are actually computed, okay, in the computation of the efficiency. Just remember this formula and how to compute for the efficiency for alternator. Actually, alternator efficiency and transformer, the formula is just the same. It's just power output over power output plus total losses. The only difference is that in the total losses, for alternator, there is the rotational losses. For transformer, there is no rotational losses. Transformer is actually a stationary machine. Okay, the only one moving there is actually the flux circulating on the core that connects the primary and the secondary. But for physical movement, there is no physical movement. But for alternators, we needed a physical movement, and that physical movement is actually rotation. That's why when they say the dam is very low in water, of course the rotation of the generator alternator is not so much. That's why we got it brought up, right? So the main thing here is that there should be so much water for us to have a prime mover for the alternator to generate voltage. Okay, let's try to discuss how the rotational losses are actually computed or known in the computation of the so-called efficiency. For the rotational losses, there are 5. Number 1 is the friction and windage. Number 2, brush friction at the field collection rings. It is here. So this refers to the excitation part of the alternator, the one that produces the current for the field excitation, for the what they call this production of the magnetic flux that is being cut by the conductors that is rotating. There is a brush friction. Brush friction is actually just like a magnetic thing in which there is a metal thing that is in contact with it as it rotates. So as it rotates, okay, whether we like it or not, the brush contacts are actually connected to the stator of the alternator. So whatever generated voltage in the winding will be collected by the brushes. So if there is a metal thing which is in contact with that brush at any time, okay, it will collect the so-called what they call this generated voltage. And if there is a contact, there should be a what they call this brush friction. Okay? We term that one as brush friction at the collection rings. Letter C, it's just the ventilation to cool the machine. Ventilation to cool the machine. How we design this concept, ventilation to cool the machine. That is considered to be one of the rotational losses. Of course, there could be some electric pulse maybe cooling of the alternator, and that is considered rotational losses. And number 4, the so-called hysteresis in eddy currents and the stator. The hysteresis in eddy currents in the transformer is the same as the hysteresis in eddy currents and the stator. It is actually the current, okay, current loss due to the, what we call this, interaction of the magnetic flux to the conductor, and that is referred to as the hysteresis in eddy currents in the stator, and that is considered to be rotational losses. I think for the friction and windage, if there are some problems involving efficiency of alternator, this is just given as a certain percent maybe. Brush friction, theoretically speaking, I don't know if we could compute for the brush friction, but I think this is also given as a certain percentage. For the ventilation to cool the machine, it is still given as just a percentage of something, right? Even I think the hysteresis in eddy current, it is given as the so-called certain percentage. So don't be bothered by the computation of the rotational losses, because there could be problems, okay? And the poor indications here, poor losses here indicated here is just given as a certain percentage of something, you know. Okay? For the electrical losses, we are familiar with this because for transformer, the total losses of the transformer are all electrical losses. And in here, we got 3 electrical losses. It's the field winding loss, the armature winding loss, and the brass contacts. For the field winding loss, it is this portion here. There is a resistance, okay, of the DC generator. There is a resistance which is connected in series with the DC generator, okay? So if there is a resistance, and since there is a current emanating from the DC generator, if we try to multiply this current here, multiplied by this area here, that is termed to as the field winding loss. Okay? There is a resistance in series with the DC generator on the field winding circuit. How about the armature winding loss? It is just given by this one. We are familiar with this because if the alternator is connected Y, right? If it is Y, there are 3 armature windings, and these armature windings are actually balanced. Okay? So if we know the armature current IA, and we know the resistance of the armature winding, like what we did from the last concept, lesson number 64, in the computation of the percent voltage segregation, we computed RE over there. So if we try to bring out the square of the armature current and the armature resistance, which is very negligible, that is termed to as the so-called armature winding loss. Okay? For the brass contacts, I don't know if there is a formula on how to compute for the brass contacts. How come this falls under electrical losses? I think this is just given a certain percentage also if there is a value for a brass contact loss. Okay? If the problem is specify a value for a brass contact, I don't think so that we could compute for the brass contact by using a formula. So it will just give maybe a certain percentage of the value of anything to compute for the brass contacts. So these are the electrical losses. So we are familiar with this one. For the field winding loss, the product of voltage and current is actually power, and this is power loss. And the square of the current times RF is still a power loss. So in the computation of the field winding, if we know the voltage E sub F times I sub F, we will multiply that and that will be computed as the field winding loss. If we try to square the field current times the value of the field resistance, that is still considered to be the field winding loss. For the armature winding loss, it is just the square of the armature current times the armature resistance. This is multiplied by small letter n, and this small letter n is actually, if the alternator is 3-phase, this should be 3. Okay? So at least we now know where this rotational losses emanates, for this electrical losses emanates, and the third and fourth losses are actually the losses in the exciter. Losses in the exciter, in the field excitation, I think this is the one already. For the stray load loss, it is just the loss if we try to bring out the concept of stray load loss. Stray. This is actually indeterminate. It's hard. This is hard to determine. But you try to Google this one. Stray load loss actually emanates from eddy currents in the armature copper conductors. From the eddy currents. Since there are currents in the armature copper conductor, and it interacts with the field winding. The field winding is actually something like this. If this is north and this is south, this is the normal field winding. But if this is the stator, there could be conductors also here. Okay? As it cuts the magnetic field winding, the magnetic field winding will have to be so-called a distorted thing due to this stray load loss, due to the current passing through the armature conductor. Okay, so the term to stray load loss is actually due to the so-called distortion of the magnetic flux due to the current passing through the, what do you call this, armature conductors. And that is termed to as a stray load loss. So it was placed here, cause distorted magnetic field. That is termed to as stray load loss. I think this is just also given as a certain percentage maybe. If somebody tries to give you a problem on the computation of the efficiency, the stray load loss might just be given as a certain percentage of a certain watts maybe on the given problem. So this is just the figure illustrating the total alternator. This is just a simplified one. I just show you two, what you call this, brass contacts. But in reality, if at the end of the stator or the armature, these are the brass contacts. Actually, if it is three-phase, the line number 1 might be here, line number 2 might be here, and line number 3 might be here. Okay? So as the armature rotates, okay, as the armature rotates, considering two conductors at any given time, there could be an alternating current voltage that is produced every 2 lines. So that's the first one maybe, the second one will be this, and the third one might be this. And this is the graph of the so-called generated voltage. So this is just a simplified one. There should be 3 lines here, but like what I said, if this is the end of the armature, the brushes are here, and for a 3-phase, the 3 lines coming out going to the step-up transformer is actually, this would be line number 1, this should be line number 2, 120 degrees apart, and this should be line number 3. So this is just a simplified view to show you a, what do you call this, It seems this is just a single piece alternator, but I am telling you this is just a simplified view. In reality, the three windings are actually spaced 120 degrees apart around the circumference of the brushes that is coming out from the armature. Okay, that's it guys. That's how we compute the efficiency of an alternator. And actually, we have discussed also how the rotation losses and electrical losses are to be determined if we try to compute efficiency. Okay, good morning from Los Angeles. This is Professor Levigator.